In this problem, again, we're given two situations, similar, and for each situation, we need to determine this applied force P needed to cause impending motion of this block. And we're also given the coefficient of static friction between the block and the surface. So the method to solve these two problems are the same. The key is to recognize that this force is likely to cause two possible impending motions. The first one is to make this block slide on the surface, and the second one is to make this block tip over. So I'm going to evaluate the P needed in order to make the block slide and the P needed in order to make this block tip over. And then I will compare these two P values and then determine exactly what kind of impending motion will occur. So for the first situation, we said that we're going to assume that, so let me say, assume sliding occurs according to the free body diagram. We have P right here. The weight force is right here at the center, 200 Newton. Normal force, don't know where it is. And this is the frictional force. Impending motion is to the right. Frictional force tries to prevent that, therefore to the left. So, resultant force along the x direction when sliding is about to happen, equilibrium equations still apply. Therefore, along the x direction, P minus FF equals to 0. Along the y direction, normal force minus 200 equals to 0. And because sliding is going to occur, that is when the static frictional force indeed reaches the maximum static frictional force, which is mu Sn. And in this case, this equals to 0.3 n. And now you realize that, well, we have three equations, three unknowns, P, FF, and N. So we can solve for all three of them. So in this case, we can solve for P to be, let's call it P1, because that's the first P, 60 Newton. But we're not done yet because I have to consider the second situation. We're going to assume tipping over happens. So now when we draw the free body diagram, it's going to be a little bit different. The weight force is still the same. The P force is still the same. However, when tipping over is about to happen, the normal force is placed at the corner. And for this situation, frictional force actually does not matter. So this corner right here, let me call it point A. We can skip the force equilibrium equations, but to write a moment equilibrium equation about point A. We couldn't do that for the previous case, by the way. For this case, we cannot write a third moment equation. The reason is because in this case, we do not know the location of the normal force. But because we are assuming tipping over is going to occur, so we do know the location of the normal force that must be at the corner. Therefore, with that specified location, we can summarize the moment about point A. Normal force and frictional force do not have moment about point A. Therefore, that only has 200 Newton force multiplied by half of this distance, 1 meter, which is 0.5 meter. The reason is because if this is a uniform block, then point G, the center of gravity, is right here. Therefore, 200 times 0.5 minus P times this distance, which is 2 meter, equals to 0. So from there, we can solve for P. This is P2 for the second situation to be 50 Newton. So because P1 is bigger than P2. In other words, P2 is the smaller one. Therefore, P2 is the minimum force needed to cause impending motion, because the problem statement didn't ask you what kind of motion. So when P is only 50 Newton, the box would already be moving and the motion is tipping over. Therefore, this is the final answer, and the motion is tipping over. All right, let's do this second problem right here real quick. Similarly, at first we assume sliding occurs. Therefore, according to this free body diagram, this is P, 100 Newton force here. Do not know where normal force is. Frictional force is here. According to equilibrium equations, because the forces along the y direction equals to 0, from there we can solve for the normal force to be 100 Newton. Because sliding is about to occur, your frictional force does equal to mu Sn, which equals to 0.4 times 100, which equals to 40 Newton. Then along the x direction, resultant force is 0. Therefore, P1 can be solved to be 40 Newton. However, if tipping over is going to occur, you have to redraw the free body diagram, because now, even though these are still the same, normal force now is placed at the corner, called point A. In this case, the frictional force actually does not matter. All you need is a moment equilibrium equation about point A. And that equals to 100 times half of this distance, because again, point G is right here. So weight force is right here. Half of this distance is 0.15 meter minus P multiplied by its moment arm about point A. Point A is right here at the corner, and that is 1 equals to 0. From there, P2 can be solved to be 50 Newton. So as you can see, P2 actually is bigger than P1, which means that P1 is the smaller one. Therefore, as a result, P equals to 40 Newton, and the impending motion is sliding.